looking at different types of sharks. Some are sleek and streamlined, like an airplane. Others are shaped like a blimp. But why is that? A St. Louis University researcher dives in for answers.
Lurking in deep blue oceans or swift and sleek near shore, sharks are frightening and exhilarating, both loved and dreaded. There are hundreds of shark species all over the world.
We just never know what we're going to see out here, and we have had some amazing discoveries.
Physics professor Jean Potvin has joined researchers from around the globe, logging many hours by boat and in the lab to study hydrodynamics. It's his specialty.
So I study the motion of fluids about objects that move through them. For example, a submarine going through the water, airplanes flying through the air, parachutes falling through the air, and sharks swimming through the water.
His colleagues at Murdoch University in Australia and the Hopkins Marine Station of Stanford University worked with Potvin on sharks before, but this time wanted something different.
These guys came back to me and said, hey, we have another problem. We're trying to explain why some sharks are shaped like torpedoes or fast airplanes, highly streamlined bodies, versus other sharks, like the white sharks, like the Greenland sharks, who are more blimpy in shape. So why is that? Being the drag guy, came with this explanation that it turns out that the difference may be due to the drag that each kind generates.
Potvin explains it's about the energetics of shark swimming and its relationship to buoyancy, along with the drag force they generate when they swim.
The blimpy sharks, we found, tend to live in cold water, versus the torpedo-shaped sharks tend to live in the tropics near the surface.
They discovered sharks evolved attributes of aircrafts to suit their habitats. For the physical modeling, he used hydrodynamics calculations that are borrowed from aircraft performance analysis.
The cold water sharks tend to prey on slower fish, which require slower speed in order to catch them. It turns out that the difference has to do with the fact that the blimpy sharks move slowly, therefore, to catch their prey. The torpedo-like tropical sharks who have to move fast and accelerate swiftly in order to catch swift prey. The hydrodynamics of drag in each case is different. For the slow-moving sharks, you can get away with being shaped like a blimp. Because you're moving slowly, you're not generating a lot of drag to start with. With the torpedo-like sharks, you're moving fast, you're accelerating fast, and that means generating a lot of drag. And the only way to reduce that drag is to be shaped like a javelin. If you were to do this shaped like a football or a blimp, it will cost you a lot more energy.
Their research shows how sharks are negatively buoyant, meaning they sink. Through evolution, Potvin shows how sharks developed larger livers. It's the colored part of the shark in his diagram.
Sharks have evolved a low-density liver.
Potvin refers to the shark liver as a partial buoyancy compensator. Sharks living in deep, cold waters evolved to have a blimp shape along with a low metabolism. They grew huge, fatty livers, taking up to 30% of their body volume, which gives them some buoyancy. As they evolved large livers, they became bulkier and less hydrodynamic. Their drag is reduced by swimming at slower speeds. The liver enables them to swim at slow speeds without sinking. Potvin compares their body shape to a zeppelin.
It's always about energy. It's always about being as efficient as possible in order to survive in the environment that you're in.
The livers of faster sharks in warmer, shallower waters are comparatively smaller in liver volume. This makes them more negatively buoyant. To avoid sinking, they have to move at high speeds. So Potvin says they are built like a javelin, fitting for an environment where everything moves faster, including their prey. Understanding the evolution of sharks may help conservation efforts.
In the context of climate change, for example, knowing how animals live and how they react or how they live in waters of given temperatures, you can start guessing what may happen if the waters are getting warmer. Which species will be more successful at negotiating climate change?
For HEC, I'm Kathleen Berger.